Hello everyone, I want to start out by saying that I find programming in Ruby to be very fun and a very powerful programming language that seems to have a couple of hidden features. One of those features is the use of threads. I have not used threads in my personal experience of programming in Ruby, but find them very interesting and hoping to start using them sometime soon. From my research with threads, I found that writing threaded code in Ruby is not as hard as it sounds or seems at first. The most important part of using threads in Ruby is understanding when to use them. A thread is a sequence of Ruby statements that run or appear to run in parallel with the main sequence of statements that the interpreter is running. Threads are implemented within the Ruby interpreter. That makes the Ruby threads completely portable, and they don't rely on the operating system. At the same time, programmers don't get certain benefits from having native threads. This means that they may experience thread starvation. That's where a low priority thread doesn't get a chance to run. If they get their threads deadlocked, the whole process may grind to a halt, and if some threads happen to make a call to the operating system that takes a long time to complete, all threads will hang until the interpreter gets control back. Finally, if their machine has more than one processor, Ruby threads won't take advantage of that fact, because they run in one process and have a single narrative thread. They are constrained to run on one processor at a time. Nevertheless, Ruby threads are efficient and lightweight way to achieve parallelism in your code. MRI has a global interpreter lock, often called GIL, and having a high level of understanding of it is important in learning how to write multi-threaded code in Ruby. The GIL prevents multiple Ruby threads from being executed at the same time. This means no matter how many threads a user spawns or how many cores they have at their disposal, MRI will never be executing Ruby code in multiple threads concurrently. But a typical Ruby program will spend a significant amount of time not executing Ruby code, specifically waiting on blocking I/O. This could be waiting for HTTP requests, database queries, or file system operations to complete. While waiting for these operations to complete, the GIL will allow another thread to execute. Programmers can take advantage of this and perform other work which doesn't depend on the result while they wait for the I/O to finish. Some examples of Ruby projects you may already know which make use of threads for performance reasons are Puma Web Server and Bundler. At Thoughtbot, they have a simple search service which takes a search term and searches across a few other internal services and presents the result in a segmented way. This searching is performed via API calls over HTTPS to various services. The results from one service don't in any way affect the results from another service, but they were performing the searches serially, waiting for each one to complete before starting the next. Since they were waiting until each search ended before they started the next one, the fastest that they were able to run the searches was the total time of the API responses from the different services plus time spent handling the incoming requests, stitching together the results, and returning a response to the end user. They still needed to wait until they got all the results from each search before they could output the final result, but found this to be a great place to use threads, performing the various HTTP requests concurrently. The wait time was able to be reduced down to the amount of time that it took to handle the slowest API request. This was their original code for calling the searches. This iterates over each of their search services, calling search.results, which is where the API request happens, and the method returns a list of result set instances, a thin wrapper around the search results. Now to see the changes to the code to make it use threads. Calling thread.new with a block creates a new thread separating from the main thread's execution and executes the past block in the new thread. Their first map returns a list of threaded instances which then map over, calling value on each. The value method does two things. First, it changes the main thread to wait for their child thread to complete using join. Creating threads without calling join on them will cause the main thread to continue without waiting and possibly exit before the children threads have finished, killing them in the process. Secondly, value returns the result of the block or raises the exception if there is any, which causes the thread to terminate. Here are the results they found from changing their code to use threads. As predicted, the overall time of the multi-threaded version correlates with the time taken for the slowest of the underlying services to return. This was a quick and simple example of how threads in Ruby can be used to help improve the efficiency of a program. Now I'm going to get more into how a programmer can start writing their own programming using threads. New threads are created with the thread.new call. It is given a block that contains the code to be run in the new thread. The newly created thread will exit when the block exits. The kernel.sleep method is used to suspend the current thread for the duration of seconds, which may be any number, including a float with fractional seconds that is passed to it. The method returns the actual number of seconds slept, rounded up. 0 arguments can cause sleep to sleep forever. When a programmer creates a thread, it can access any variables that were within the scope at that point. However, any local variables that they are then created within the thread are entirely local to that thread. They can pass any number of arguments into the block via thread.new. Why does a programmer call join on each of these threads they create? When a program terminates, all threads are killed regardless of their states. However, a programmer can wait for a particular thread to finish by calling that thread's thread.join method. The calling will block until the given thread is finished. By calling join on all the requester's threads, they can make sure that all the requests have completed before terminating the main program. The thread class has several class methods that serve various purposes. The thread.main method returns a reference to the main thread, which spawns the other threads. The thread.list method returns an array of thread objects for all threads that are either runnable or stopped. The thread.current method returns the currently executing thread. The thread.kill, thread.pass, thread.exit, thread.start, and thread.stop methods are used to control the execution of threads, often from inside or outside. The thread.kill method causes the given thread to exit. The thread.pass method invokes the thread scheduler to pass the execution to another thread. The thread.exit method terminates the currently running thread and searches another thread to be run. If this thread is already marked to be killed, thread.exit returns that thread. If this is the main thread or the last thread, exit the process. The thread.start method is basically the same as the thread.new. The thread.stop method stops execution of the current thread, putting it to sleep into a sleep state, and schedules execution for another thread. Note that there's no instance method stop, so a thread can stop itself, but not another thread. What is the need for thread exclusion? An example of a need for thread exclusion involves an electronic banking application. Suppose one thread is processing a transfer of money from a savings account to a checking account, and another thread is generating monthly reports to be sent out to the customer. Without proper exclusion, the report generation thread might read the customer's account data after the funds have been subtracted from their savings, but not before it's been added to their checking. In summary, Ruby threads are a lot easier for programmers to use than they may seem at first. If they are used correctly, they are very helpful in improving the efficiency of a code that has different I/O operations or other operations that take place outside of the code, like retrieving data. This is all good, but it is easy for a programmer to forget to do a couple of steps and make threads useless, like forgetting to join their threads so their program ends before the threads finish. Threads are very useful, and I can't wait to get a chance to use them.